Okay, electronegativity, bond polarity. So the Lewis dot model is very simple, and that's great, but it's also just very simple, and you kind of just have this gut feeling that it can't really be that simple. It is an oversimplification. So the electrons are shared, but they're not necessarily shared equally. So we have polar covalent bonds. Polar covalent bonds have unequal sharing. This is like, the older brother and the younger brother are supposed to share the cookie, right? And this is like a 1-year-old little brother. And so big brother breaks the cookie, but it's not exactly in half, right? He gives the smaller piece to the little brother. Little brother is too young to notice that it isn't exactly half because his brain just doesn't process stuff like that yet. And so he's okay, he got some cookie. Big brother got more cookie. Mom says, hey. Brother says, you said share, I shared. It wasn't equal sharing though, right? That happens a lot, huh? You share a bed with someone and they kind of pull the covers. Some of you are the bedclothes hogs and others are the ones that lose all the blankets every night, right? It happens. That happens with sharing of electrons as well. It's not always equal. So when you have unequal sharing, this gives us a bond that's kind of between an ionic bond and a pure covalent bond. A pure covalent bond, you have exactly equal sharing, like between 2 chlorine atoms. They are the same, and so they're going to share the electrons the same. Something like hydrogen fluoride. We can represent it this way or like this. The fluorine has a stronger attraction for the electrons. So in that shared bond, the fluorine is hogging the electrons. And so that gives rise to the fluorine end of this molecule being slightly negative and the hydrogen end slightly positive. It's not an ionic compound. So this lowercase Greek delta means a partial negative charge, and this is a partial positive charge. So you could say, well, this is maybe a 0.1 negative. It's not 1 minus, it's 0.1 minus. And this would be then 0.1 plus. It's just a little bit. But if you put this in an electric field, here's no electric field. These molecules are arranged randomly. If you turn this electric field on and you have a positive and a negative charged plate, the negative, all these molecules are going to line up. And you can get them to do that, and all the negative ends will be pointing towards the positive plate, the positive ends towards the negative plate. So this is another way of representing it. The plus end over here is the positive side, and it points to the negative side. I think of this as, electrons remind me of little boys, especially Andrew. They're squirrely and they're very energetic and they're always running around doing stuff. So let's think about 2 little boys. They live next door to each other and they're going to play together, right? So they can play at hydrogen's house or they can play at fluorine's house. So hydrogen's house, they've got an old black and white television and a VHS recorder and some old Thomas the Tank Engine tapes. And if you're hungry, the mom will give you some bread and some tap water. It's like, it makes your stomach stop growling, but it's not exactly fun. Over here at Fluorine's house, they have a swimming pool with a slide. They have every cable channel. They have the big screen TV. They've got all the video games. They actually have a soda fountain in the kitchen. I was in Oslo for a week. I saw 1 soda fountain. That's why I also saw very few large people. Okay, they don't drink soda like that. They drink it out of the bottles. They buy 1 bottle and that's all. Yeah. Anyway, but this is a fun place to be. If you're hungry, the mom will order pizza delivered to the house, and there's a soda fountain you can have all you want. Where are those 2 little boys going to spend more time? At Fluorine's house. Why? It's more attractive, right? So I think of this arrow as like dad's coming home and he's like, where are the boys playing? And it's the neighbor standing out and he points over there. So this is the neighbor pointing. He's pointing to the more attractive to electrons side. Attraction for electrons in a covalent bond is called electronegativity. It causes an imbalance in the electron cloud. So this end, there's just, the electrons are over there more than they are over here. It's lopsided, it's not symmetrical. So we can define electronegativity as the ability of an atom to attract electrons to itself in a chemical bond. This is inversely related to atomic size. For the same reason that we have this relationship with lattice energy and size. So, or ionization energy and size. A smaller atom is going to have a larger electronegativity than a larger atom. Fluorine is the most electronegative element. And that's something, just remember that. And as we get closer to fluorine, things become more electronegative. The noble gases are so unreactive that we just don't even include them in talking about electronegativity, because there's very, very few compounds that they actually make. So we just leave them out of this. Whoops. So this is a diagram, a chart showing trends in electronegativity. So the height of the column shows more electronegative. And so here's fluorine. He's king of the hill, top of the heap. That's the coolest place for the electrons, the most attractive to the electrons. And you know, down over here, you've got things like francium, just not a very fun place to be. So the trend is, as you go closer to fluorine, higher in electronegativity. So if you're going across, electronegativity increases. As you're going up a column, it increases. Going down a column, it decreases. So how close are you to fluorine? Who's closer to fluorine? That's more electronegative. These are the actual values. Fluorine was given a value of 4.0 because, you know, you got to have a scale, right? And so it's just like a grade point average or something. Fluorine's got the straight 4.0. And we can look at differences in electronegativity by comparing the numbers. And you may need to do that on a homework assignment or possibly on a worksheet. But this is not something you would memorize. The only thing I would like you to know is there are some different elements that have the same electronegativity, like carbon and sulfur. They do have the same electronegativity. So carbon and sulfur would share their electrons evenly. Okay? I don't expect you to remember which ones those are. So polar bonds, unequal sharing. Of course, you can have severely unequal or just a little bit unequal. There's a scale. So this is representing from, come on, there, from 0, difference in electronegativity, up to, come on, you can do it. There you go, 3.3. So it's a continuum. So we talk about nonpolar bonds. The book also calls them pure covalent bonds. I prefer nonpolar. We can have polar covalent bonds where there's unequal sharing, there's a difference in electronegativity. And then ionic bonds are like the extreme version where the kid from that one house that doesn't have much fun stuff decides he's just going to go live at the other kid's house. There's an actual transfer of electrons. He just stays over there all the time. Okay, so that's an ionic bond. So where do you draw the line in between? Well, it's kind of arbitrary, and I'm not going to get hung up on exactly where it ends up being. Homework problems could get hung up on that. So we say that if the difference in electronegativity is 0.4 or less, we call that a nonpolar bond. If it's above 0.4 up to about 2.0 in difference, then it's a polar covalent bond. The electrons are shared but not equally. And if the difference is over 2, then it's an ionic bond. They're transferred. Because in actuality, an ionic compound, it's not a complete transfer. But for Chem 1A, we can think of it that way. So any questions? It's, you know, it's a little bit like saying, well, you know, who's poor and who's rich? You know, how do you decide? It's arbitrary, right? So you kind of look at it and say, well, there's this group and then there's this middle group. It's sort of like the upper class, the middle class, and the lower class, right? The definition is a bit arbitrary. Well, we can get more quantitative about this. We can talk about dipole moment. A dipole moment is something that occurs anytime you have a separation of positive and negative charges. So when you separate positive and negative charges, they don't like to be separated. And so that can be measured as mu, the dipole moment, equals Q times R, where Q is the charge magnitude and R is the distance between them. And the unit that's used for this commonly is called the debye, and it has a capital D, and it's equal to this many coulombs times meters. So I want you to have seen that that is a unit. We're really not going to use it. We're really not going to use this equation. But there are parts of chemistry where they do use that. So here we can look at some different molecules and look at the difference in electronegativity between the two atoms. So this is two chlorine atoms. The difference in electronegativity is going to be 0 because they're the same, right? And so we see that the dipole moment, come on, pointer, is 0. Here, chlorine and fluorine. If we go back to the table, fluorine is a 4, chlorine is a 3. So the difference in electronegativity, 4 minus 3 equals 1, right? So the change in difference in electronegativity is 1, and this has a dipole moment of 0.88. The dipole moment does not equal the difference in electronegativity because there's also this R in here. So the sizes of the ions or the atoms have an effect on this. Here we've got HF and LF. Okay, so we can look at the numbers. This is what I would like you to be able to do. So just looking at a formula of a diatomic a molecule, you should be able to tell me whether it's polar, nonpolar, or ionic. So ionic is like this one. I can tell you that that's ionic without looking at electronegativity differences, because lithium is a metal and fluorine is a nonmetal. And we've already learned to name those as ionic compounds. So this is going to be ionic because it's metal and nonmetal. This one is nonpolar. No polar. Nonpolar. I know that because chlorine and chlorine, they're the same. If you have two identical elements, they're going to be nonpolar. Both of these I would expect you to tell me are polar. Because here what we've got is, well, this is two of the same element. And these are going to be polar, and polar is two nonmetals, two different nonmetals. I didn't do that very well, but I think you get the idea. So two of the same element, that bond is polar, nonpolar. Two different nonmetals, I would expect you to predict that that's polar. Now, occasionally you might be wrong. Those chances are very, very small. Like carbon and sulfur, that's a nonpolar bond, even though it's two different elements. But we're not going to worry about that. We're going for most of the time. If you have a metal and nonmetal, you should tell me that's an ionic bond. That's an extreme of the polar. We can also talk about percent ionic character, and that would be the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. So if this was ionic, would be the whole thing, and what it actually is the part over the whole times 100. And so here's a graph showing percent ionic character versus electronegativity difference. So we say that if it's over 50% ionic character, we're going to call it an ionic bond. There's no bond that's actually 100% ionic. Like I said, it's helpful to think of it that way, but it really isn't quite. So we see that we have these two clusters, right? We have a cluster down here, and we have a cluster up here. What do you notice that these things down here have in common? What kind of elements are in those compounds? All nonmetals, right? Two different nonmetals are going to have a difference in electronegativity. They're going to be polar, but it's just going to be a little bit. So these guys are all below 25. Up here, above 50%, these are all metals and nonmetals. We've got this one guy in here, HF. Hydrogen is a nonmetal with one of the lowest electronegativities for nonmetals, and fluorine is the highest. But this is still not ionic because it's below 50%. So there that is. Any questions? So we should be able to do this. Determine whether the bond formed between each pair is, I don't like that word, pure covalent, nonpolar, polar, or ionic. So between iodine and iodine, is there any electronegativity difference between those two? No, because they're the same. So this is a nonpolar bond. It would be a nonpolar covalent. How about between cesium and bromine? What kind of elements are they? Metal and nonmetal. So what does that make it? Ionic. We don't have to look at a table of electronegativities to tell us that. This is ionic. How about phosphorus and oxygen? Both nonmetals. They're not the same. Probably 90% of the time, that's going to be a polar covalent bond. They're sharing, but not exactly equally. Any questions?